We're going to tie together several ideas that we've spoken about before. So the title of what we're going to be talking about is called the Empirical Rule. And I want to emphasize a couple of things. The empirical rule only works if we have bell-shaped distributions. So go ahead and draw for me on your paper this kind of bell curve shape. And all that means is it's symmetric, the left and right are mirror images, it's unimodal, kind of one mode right in the middle. And if data set follows this bell-shaped distribution, then we can apply the empirical rule to approximate areas under this bell-shaped curve. So if you remember before, when we have symmetric data, the preferred measure of center for symmetric data is the mean. So I'm just going to kind of eyeball, and if you remember, our notation for the mean of data is x bar. So there's the mean of the data, my preferred measure of center for this distribution. The preferred measure of spread for symmetric data, if you remember, was the standard deviation, how far observations are on average from this mean or balance point. So this empirical rule gives me an approximation. I want to emphasize that. If I go up one standard deviation from the mean, and we'll do this in context in a moment. So here's the mean of the data. If I add a standard deviation to that scale, and I subtract a standard deviation, so these are S's representing standard deviation. So if I start at the mean and I create an interval that's one standard deviation on either side, then this empirical rule tells me I should have 68% of my observations, approximately. Sorry, that's a little messy. That's a 68%. So again, remembering this is symmetric, if I have 68% in the middle, then in either piece, just split that in half, I should have 34% on either side. All right, if we go another standard deviation in either direction, so add a standard deviation here, and subtract another standard deviation here. So now this interval represents I've gone up 2 standard deviations and back 2 standard deviations from the mean. Then I should have, remember this is all approximately, should have about 95% of my data in that interval. About 95% of observations between 2 standard deviations on either side of the mean. Now, from 68 to 95, we've added a certain percentage. If we split that in half, think for a moment, what are we going to have left on either side? Right, should be 13.5%. Now let's do this one more time. If we go up and back a third standard deviation, so subtract a standard deviation here, add a standard deviation here, then we should have, within 3 standard deviations of the mean, we should have about, I've been saying about all the time, now I'm going to write down this little squiggle here to mean approximately 100% of the data. And I really want to emphasize that it's approximately, because it doesn't mean we can't have data beyond this. In fact, we do. It's just very, very rare. The percentage of the time is so small, I'm not going to worry about writing it down. Even though some other textbooks might do that, note, it is possible to get beyond 3 standard deviations. It's just pretty rare. So we're going to say almost all of it is within 3 standard deviations. So let's apply this to a particular setting. So in this setting, we've got several athletes, 11,000 from the 2012 London Olympics. There's a fun link here if you want to look at that later. You can separate by sport, sex of the individual, and so on. So we have a large number of observations, and they tell us the average age was 25 years old. So I know when I draw this distribution, first we know here it says the ages are unimodal and symmetric. So that's my green light. Unimodal and symmetric says draw this bell curve. Just another way to say bell curve. One mode and it's symmetric. So I've drawn my bell curve. They tell us the average age is 25 years old. So I'm going to put that in the middle. My average age, 25 years old. Then the percentages stay exactly the same as we had on our introductory picture a moment ago. The only thing that changes, we need to actually use the mean and standard deviation to plug in. So centered at 25 years old, standard deviation, that's our S, of 3.5 years. So if I do 25 plus 3.5, we get 28.5 years. And then minus 3.5, we get 21.5 years. And according to this empirical rule, we've got about 34% in either of these pieces. 34% of observations fall here, 34 here. So altogether, about 68% of my data points fall in this range. Let's go out again. So if I add another 3.5 to this, we'll get 32. If I subtract 3.5, we're going to end up at 18. So now, according to our empirical rule, about 95% of observations are between 18 and 32, 95% of the data points in this range, and that gave us another 13.5 in either of these pieces. Okay, and then our last one, if we go out yet one more standard deviation, so 18 minus 3.5, we're going to get 14.5. And then 32 plus 3.5, we'll get our 35.5. And that should give us about all of our data. So we went from 95% to about 100%, which will give us 2.5% in each of these. 5% left over, split it up equally. All right, so once you've drawn the picture, even if the homework problem does not ask you to draw the picture, I would highly recommend it because now it's going to be really easy to answer some questions using our picture. So for example, what percent of athletes are younger than 18? We're going to look at, here's 18 years old. Look at all the area younger than that. So this part, 2.5%. are younger than 18. Next question, older than 28.5 years old. So here's 28.5. If I add up all the areas that are greater than that, all the ages that are above that, then I've got my 13.5 plus 2.5 will give us our 16% are older than 28.5. Then, what if I ask the next question, between 21.5 and 32 years old? Same thing, let's add that up, between 21.5 and 32. Right, we should get our 81.5%. All right, the last question changes it up a little bit, and I want to make sure you're good with this idea of percentile. When we talk about percentile, I guess maybe the most common definition or example is maybe standardized test. If you score in the 75th percentile, that means you scored better than 75% of people, and 25% did better than you. So percentile specifically means that percent or area is to the left or below. So maybe draw a picture here. I'll just put some, okay, so maybe this value, whatever it is, would be my 10th percentile, is the value that gives me 10% of the area to the left, below. The definition never changes. We never mean the area is going to be up here when we say percentile, always down here. And we're looking for what's the x value, what's the observation that gives us that area below. So, for example, my first son, was a preemie, and for a while there, he was like 0th percentile for length, meaning he was as short as they come. And then for weight, though, he was like the 40th percentile. He was a little bowling ball. He was doing pretty good on the weight category. Okay, so for this example, 2 parts to the question. What age is the 50th percentile? So what age has half the area below? That one should be easy. The mean, this is symmetric. So 25 years old has 50% of the area below it. The 84th percentile wants to know which age has 84% of the area below it. So if we look at this, we know when we get to 25, that's half the area below it. Now I need to get up to 84. So if I go one more, 28 and a half, there's 34%. So 28 and a half years old has 84% of the area below it. Let me just give you a couple more to double check here. What if I asked for the 16th percentile? Hopefully you're thinking 21 and a half because it has 16% of the area below it. 21 and a half is the 16th percentile. What if I asked for the 97.5th percentile? Right, we want the age that has 97 and a half below it, so that would be 32. Has 2.5 above, 97 and a half below. And then last one, what if I asked for the 0th percentile? Hopefully you'd say that's 14 and a half. It has about 0% below it. But remember, 0 is not technically correct. There is some stuff down here, and up here, it's just very little.